What if everything you see around you, the stars, the planets, even the space between them, is being shaped by forces you can't see? Forces so subtle they slip past our senses, yet so powerful they guide the very architecture of the universe. These are the invisible sculptors of space-time, fields and energies that work in the background of reality, carving out the shape of everything from the smallest particles to the largest clusters of galaxies. Think about that for a moment. Light doesn't just travel in straight lines, it bends around massive objects. Time doesn't always flow at the same rate, it stretches and warps. Galaxies spin in ways that shouldn't be possible unless something unseen is holding them together. All of these phenomena point toward a reality far richer, far stranger than what meets the eye. For centuries, humans have looked up at the night sky and wondered how it all works. We built myths, crafted instruments, and developed profound theories to make sense of the cosmos. But just when we thought we had it all figured out thanks to brilliant minds like Einstein, new mysteries emerged. Mysteries that can't be explained by matter and energy alone. Something else is at work, something silent, pervasive, and deeply mysterious. These invisible fields may be the missing piece in our understanding of the universe. They don't just fill empty space, they define it. They don't just influence matter, they generate it, and in doing so, they may hold the key to questions we've been asking since the dawn of curiosity itself. Why is the universe the way it is? What is reality, really, and how did it come to be? In this video, we're going to explore these profound questions together. We'll travel from the enormous scales of galaxy formation down to the frenetic quantum foam where particles blink in and out of existence. We'll look at how gravity warps space-time, how dark matter provides a hidden scaffold for cosmic structures, and how dark energy is relentlessly pushing the universe apart. We'll dive into theories like inflation, quantum fields, and even the holographic principle, ideas that sound like science fiction but are at the frontier of today's physics. This isn't just a story for scientists, it's a human story. It's about reimagining our place in the cosmos and rediscovering the wonder that comes from peering into the unknown. So come with us on this journey. Let's uncover the hidden architects of reality and perhaps along the way reshape how you see the universe forever. Before Einstein, we thought of space and time as separate, absolute stages where events unfolded. Space was the fixed container, time the steady tick of a universal clock. But Einstein's theory of relativity shattered that view, weaving them together into a single, dynamic entity called space-time. This isn't just a philosophical idea, it's a physical fabric that can be stretched, compressed, and warped. The mass and energy of objects like stars and planets create dents in this four-dimensional fabric. What we experience as gravity is simply the effect of moving along the curves of these dents. A planet orbiting a star isn't being pulled by some mysterious force. It's following the natural contour of the warped space-time around that star, like a marble rolling around the rim of a bowl. This curvature leads to some of the most mind-bending phenomena in the universe. Gravitational lensing, for instance, occurs when light from a distant galaxy travels toward us and has to pass through the warped space-time around a massive object like a galaxy cluster. The light doesn't travel in a straight line as we'd expect. It follows the curve, bending around the mass. This acts like a cosmic magnifying glass, distorting and sometimes even multiplying the image of the background galaxy, allowing astronomers to see objects that would otherwise be too far away. Then there's time dilation, a concept that feels pulled from science fiction but is a verified reality. Time itself flows at different rates depending on the strength of the gravitational field. A clock placed closer to a massive object will tick slower than one farther away. This isn't a mechanical error, it's a fundamental property of spacetime itself, proven by incredibly precise atomic clocks at different altitudes. To visualize all this, the most common analogy is that of a stretched rubber sheet. Imagine spacetime as this vast, elastic canvas. Now, place a heavy bowling ball in the center. The sheet dips and curves under its weight. If you then roll a smaller marble across the sheet, it won't travel in a straight line. Instead, its path will curve inward, orbiting the central mass before perhaps spiraling into it. This simple model perfectly illustrates how gravity works not as a force reaching out and grabbing things, but as a consequence of geometry. The marble isn't being pulled, it's just following the path of least resistance through the curved landscape. This foundational understanding of spacetime as a malleable fabric is the essential first step. It sets the stage for the real mystery. If the visible universe of stars and planets creates these curves, what else might be bending the sheet in ways we are only beginning to detect? But if gravity and its warping of spacetime were the whole story, our cosmic models would be complete, and the universe would behave exactly as we predict. Yet it doesn't. Galaxies rotate too fast for the visible matter they contain, and the expansion of the universe is accelerating, not slowing down. This tells us that the cosmic rubber sheet is being bent and stretched by more than just the matter we can see. It is being shaped by invisible architects. These are not objects or substances in the conventional sense, but pervasive fields that fill what we once thought of as empty space. Imagine the vacuum of space not as a true void, but as a vibrant, seething ocean of energy. Even in the deepest, darkest void between galaxies, this ocean is alive with activity. It is humming with fields that are constantly on, their presence felt through the forces they mediate and the particles they create. The most famous of these is the Higgs field. Think of it not as an empty stage, but as a kind of cosmic molasses that fills all of space. As fundamental particles move through this field, they interact with it. Some particles, like photons, zip through unaffected, which is why they have no mass and travel at the speed of light. Others, like quarks and electrons, slog through this molasses, and that act of slogging, of interacting with the field, is what we experience as their mass. Without the Higgs field, nothing would have mass. Atoms wouldn't form, stars wouldn't ignite, and the structured universe we know simply wouldn't exist. Its discovery was a monumental confirmation that invisible fields are not just mathematical tricks. They are real components of reality that dictate the most fundamental properties of matter. But the Higgs field is just one player in a much larger cast. Theoretical physics suggests a whole spectrum of these fields, each with its own unique role in the cosmic play. There's the inflaton field, a hypothetical entity believed to have powered a spectacular growth spurt in the universe's earliest moments, a period called inflation. In a fraction of a second, this field's energy stretched the fabric of spacetime itself, smoothing it out and planting the tiny seeds that would one day grow into galaxies. Then there's the field associated with dark energy, a mysterious presence causing the expansion of the universe to speed up. It acts like an anti-gravity force, not by pulling or pushing matter, but by stretching the very spacetime between galaxies. Detecting these fields directly is nearly impossible because we can't see or touch them. Instead, we witness their handiwork. We see the Higgs field's effect in the mass of particles at the Large Hadron Collider. We infer the inflaton field's past existence from the faint afterglow of the Big Bang, the cosmic microwave background. We measure dark energy's influence by watching distant supernova race away from us. These fields are the silent directors of the cosmic drama. and understanding their scripts is the key to unraveling the deepest mysteries of our existence, from the universe's first breath to its ultimate fate. Of all the invisible forces that shape our universe, gravity is the one we know best, the sculptor whose work is written across the night sky. It is the master architect of the cosmos, the first and most obvious force bending the fabric of space-time to its will. According to Einstein's theory of general relativity, this isn't some magical attraction at a distance. Instead, picture a star not as a simple ball of light, but as a profoundly heavy weight resting on that elastic sheet of space-time. Its immense mass creates a deep, smooth depression in the fabric. Now, a planet, following the natural contours of this curved landscape, doesn't feel a pull so much as it simply rolls along the groove created by the star, tracing an orbit that we have mapped for centuries. This elegant curvature is the reason our Earth circles the Sun and why the Moon circles us. It dictates the majestic dance of entire galaxies, a cosmic ballet choreographed by mass and the geometry of space-time itself. But the artistry of gravity extends far beyond simple orbits. When truly colossal events occur like two black holes locked in a final, spiraling embrace, the violence of their motion sends ripples racing outward through the very fabric of space-time. These are gravitational waves first predicted by Einstein and finally detected a century later. They are like the tremors from a sculptor's chisel, literal vibrations in the structure of reality that travel across the universe at the speed of light. We can now measure these incredibly faint signals, allowing us to observe cosmic events that are completely invisible to traditional telescopes. Gravity also dictates the dramatic final act of massive stars. When such a star exhausts its fuel, its own immense gravity turns inward, causing a catastrophic collapse. If the core is heavy enough, no known force can stop it, and it crumples into a point of infinite density, tearing a hole in space-time itself, a black hole where gravity becomes so overpowering that not even light can escape its grip. For a long time, it seemed gravity alone could explain the large-scale structure of everything we see. Yet, as our observations became more precise, a puzzle emerged. When astronomers measured how fast galaxies spin, they found the stars on the outer edges were moving far too quickly. Based on the amount of visible matter, the stars, gas, and dust we can see, the gravity at the edge shouldn't be strong enough to hold onto these stars. They should be flung off into the void, yet they aren't. It was as if we were only seeing the tip of an iceberg, with some immense, unseen mass providing the extra gravitational glue to hold the galaxy together. Furthermore, by the late 1990s, scientists made an even more startling discovery. Not only is the universe expanding, as we've known since Hubble, but this expansion is accelerating. It's speeding up. Gravity, which pulls matter together, should be putting the brakes on this expansion, causing it to slow down over time. Instead, something appears to be overpowering gravity's attractive grip on the largest scales, pushing galaxies apart at an ever-increasing rate. This is where the story deepens. Gravity, for all its power, is not working alone. It is the primary sculptor, the one whose tools we understand, but it has silent partners. The fact that gravity cannot account for the motion of galaxies or the fate of the cosmos is not a failure of the theory, but a profound clue. It is our first direct evidence that there are other, even more mysterious architects at work. These unseen partners, whether we call them dark matter or dark energy, must also be bending and stretching the cosmic canvas, subtly refining the shape of reality in ways that challenge our most fundamental models of physics. The presence of these gaps in our understanding doesn't diminish gravity's role. It illuminates it, showing us that this familiar force is just the opening chapter in a much longer and more astonishing story of cosmic creation. So if gravity is the sculptor we can see at work, carving the orbits of planets and the paths of light, then dark matter is the hidden framework, the unseen support structure that holds the entire cosmic sculpture together. We cannot see it, touch it, or interact with it in any way through the electromagnetic force. It doesn't absorb, reflect, or emit light. It is completely, utterly dark. And yet, we know it's there because of its immense gravitational footprint. Its presence is felt not in what we see, but in what we observe happening to the things we can see. The story of its discovery begins closer to home within our own galactic neighborhood. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. By measuring the speed of stars at different distances from a galaxy's center, she expected to find a familiar pattern. Think of our solar system. Mercury, the planet closest to the Sun, orbits at a blistering speed, while distant, slow-moving Neptune takes its time. This is because the Sun's gravitational grip weakens with distance. Rubin expected stars at the outer edges of a galaxy, far from the central bulge of mass, to orbit much more slowly than those near the center. But that's not what her data showed. To her astonishment, she found that stars on the very outskirts of galaxies were orbiting just as fast as those near the core. This was impossible. There simply wasn't enough visible matter, stars, gas, dust, to generate the gravity required to hold these speeding outer stars in place. According to all known physics, these galaxies should have flown apart eons ago. The only logical conclusion was that there had to be a huge amount of additional mass that we couldn't see, a massive halo of invisible matter surrounding each galaxy, providing the extra gravitational glue. This invisible mass became known as dark matter, but the evidence doesn't stop there. Dark matter also reveals itself through its ability to bend light, a phenomenon we've already touched on, gravitational lensing. When light from a distant galaxy travels through the universe, its path is bent not only by visible objects like galaxy clusters, but also by the vast concentrations of dark matter associated with them. Sometimes the distortion is so severe that the background galaxy is stretched into long, faint arcs of light, like a reflection in a funhouse mirror. By meticulously mapping these distortions, astronomers can essentially chart the distribution of the dark matter itself, creating maps of the invisible. These maps reveal that dark matter forms a colossal cosmic web, a scaffolding upon which visible matter gradually clumped together after the Big Bang. Ordinary matter, the stuff that makes up everything from stars to our own bodies, was attracted to and coalesced within these dense knots of dark matter. Without this underlying framework, the universe would lack the magnificent large-scale structure we see today, the vast filaments of galaxies stretching across billions of light years, connecting in immense clusters and surrounding great empty voids. So what is this mysterious substance? We know what it's not. It's not black holes made of ordinary matter, as searches for these so-called macho have come up short. It's not clouds of normal gas or dust. The leading candidate is a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be their own antimatter partners, and they would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Decades of experiments deep underground, shielded from cosmic rays, have tried to catch the extremely rare bump of a WIMP colliding with an atomic nucleus, but so far the detectors have remained silent. This has led physicists to broaden the search, considering other possibilities like actions or even sterile neutrinos. The hunt is one of the most compelling and challenging in all of modern science. Dark matter is the ultimate example of an invisible sculptor. It doesn't emit light, but it dictates where light will eventually form. It doesn't interact with the forces we know best, yet it has orchestrated the grand architecture of the entire visible universe. Its existence forces us to accept a humbling truth. The stuff we see and are made of is just a small fraction of what's actually out there. The majority of the cosmos is built from something entirely foreign, a hidden framework whose true nature remains one of the greatest puzzles in physics. If dark matter is the hidden framework holding the cosmos together, then dark energy is its mysterious counterpart, working in complete opposition. It is the great repulsive force, the anti-sculptor, that is stretching the very fabric of space-time on the grandest of scales. For much of the 20th century, the prevailing assumption was that the universe's expansion, set in motion by the Big Bang, was gradually slowing down. The relentless pull of gravity from all the matter in the cosmos was thought to be acting like a cosmic brake, gradually reining in that initial outward rush. The biggest question was simply whether there was enough matter to eventually halt the expansion entirely, leading to a big crunch, or if it would just continue to coast outward forever, slowing to a near standstill over trillions of years. This assumption was utterly shattered in the late 1990s. Two independent teams of astronomers were using distant stellar explosions, called Type 1a supernova, as cosmic mile markers. These supernovae have a known intrinsic brightness, so by measuring how dim they appear from Earth, scientists can precisely calculate their distance. They can also measure the redshift of their light, which tells us how much the universe has stretched since the explosion occurred. By comparing supernovae from different eras, the teams aimed to measure how much the expansion rate had slowed over billions of years. To their profound shock, the data revealed the exact opposite. The most distant, and therefore oldest, supernovae were dimmer than expected. This meant they were farther away than any model of a slowing expansion could account for. The inescapable conclusion was that the expansion of the universe wasn't slowing down at all. It was speeding up. Galaxies were flying apart from one another at an ever-increasing velocity. This discovery was so bizarre and unexpected that it earned the teams the Nobel Prize in Physics in 2011. What could possibly be causing this? The leading explanation points to a property of space itself. According to quantum physics, a vacuum is not truly empty. It is a seething foam of virtual particles constantly flickering in and out of existence. This quantum activity endows every cubic centimeter of space with a tiny, latent energy. Einstein himself had once proposed a similar concept, a cosmological constant, to balance his equations for a static universe, which he later called his greatest blunder after the expansion of the universe was discovered. Ironically, his blunder may have been a stroke of genius decades ahead of its time. If this vacuum energy is real and constant, then as the universe expands and more space comes into existence, more of this repulsive energy is created. This creates a feedback loop. More space means more dark energy, which pushes to create even more space, accelerating the expansion faster and faster. This would make dark energy an inherent property of the cosmos, woven into its very fabric. However, this elegant idea comes with a colossal problem, the cosmological constant problem. When physicists attempt to calculate the theoretical strength of this vacuum energy using quantum field theory, the value they get is absurdly, unimaginably large, about 120 orders of magnitude stronger than what we actually observe. If their calculation were correct, the repulsive force would have been so powerful in the early universe that it would have ripped apart atoms, stars, and galaxies before they could even form. The fact that we exist and can measure a much smaller, gentler effect means something is profoundly wrong. Either our understanding of quantum physics in empty space is incomplete, or dark energy isn't a constant at all. This has led to other, even more exotic theories. Perhaps dark energy is not a constant but a dynamic field, similar to the inflattened field that drove the early universe's rapid inflation. This concept, sometimes called quintessence, proposes a new, evolving energy field that permeates space. Its strength could change over time, potentially weakening or even eventually becoming attractive. Another possibility is that Einstein's theory of general relativity, while spectacularly successful on the scale of the solar system, breaks down on the scale of the entire universe. This has spurred theories of modified gravity, which attempt to explain the accelerated expansion without invoking a mysterious new energy at all. Regardless of its true nature, dark energy's role as a sculptor is undeniable and terrifying in its implications. It is reshaping the cosmic landscape on an epic scale, determining the ultimate fate of everything. If the acceleration continues unchecked, it points toward a cold, lonely end for the universe, a big freeze or heat death. In this scenario, billions of years from now, the expansion will have accelerated so much that distant galaxies will be pushed beyond our observable horizon, their light forever too stretched and faint to ever reach us. The universe will become a vast, ever-expanding emptiness, with isolated islands of galaxies growing dark and cold. Dark energy demonstrates with stunning clarity that the most powerful forces shaping our reality are not the visible structures of stars and planets, but the invisible, enigmatic properties of space itself, guiding the cosmos toward a destiny we are only beginning to comprehend. But to truly appreciate the grand cosmic sculptors like dark matter and dark energy, we must now shrink our perspective down to the most fundamental level, to a realm where the very concept of a solid, stable particle dissolves into something far more fluid and dynamic. This is the quantum world, and here the primary architects of reality are not objects but fields. Imagine the entire universe is an ocean, a vast, deep, and restless ocean. In this analogy, what we perceive as particles are not tiny, solitary specks, but rather temporary excitations of this ocean, like waves or ripples on its surface. An electron is not a miniature ball. It is a localized vibration in the universal electron field. A photon is a ripple in the electromagnetic field. Every type of fundamental particle has its own corresponding field, a fundamental entity that stretches throughout all of space and time. This is the revolutionary perspective of quantum field theory, which tells us that these fields are the true bedrock of reality, and particles are merely the way these fields manifest themselves when they have energy. This leads to one of the most bizarre and profound consequences in all of physics, the concept of vacuum fluctuations. If these quantum fields exist everywhere, then even in what we would consider a perfect vacuum, a region of space completely empty of particles, the fields are still there. And they are never truly still, due to the Heisenberg uncertainty principle, which allows for temporary borrowings of energy. These fields are constantly jittering and quivering. This quantum jitter causes tiny, spontaneous ripples to appear and then vanish almost instantly. In practical terms, this means particles and their antimatter partners are continuously popping into existence out of nothingness, existing for an unimaginably brief moment, and then annihilating each other, returning the borrowed energy to the universe. This isn't just theoretical. It's been verified through experiments like the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight, measurable force pushing them together because the number of certain vacuum fluctuations that can fit between them is limited compared to the fluctuations outside. Now consider the potential power of this ceaseless, microscopic activity. Individually, each of these quantum fluctuations is inconceivably small and fleeting. But what if their effects could add up? Some physicists speculate that this endless frothing of the quantum vacuum could be the source of the dark energy that is accelerating the expansion of the universe. In this view, the energy of these fluctuations provides a constant, pervasive pressure that pushes spacetime apart. However, as we touched on earlier, there's a massive problem with this idea. The calculated energy density of the vacuum is astronomically larger than the observed strength of dark energy. This glaring discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in theoretical physics, suggesting that either our understanding of quantum fields is incomplete or that some unknown mechanism is cancelling out almost all of this vacuum energy, leaving behind only the tiny, residual effect we call dark energy. The influence of these microsculptors might extend even further back in time, to the very origin of everything. The theory of cosmic inflation proposes that a similar quantum field, called the inflaton field, was responsible for the universe's rapid exponential expansion a fraction of a second after the Big Bang. According to this idea, tiny quantum fluctuations in this primordial field were stretched to enormous sizes by the inflationary expansion. These stretched-out irregularities became the seeds for all future structure in the universe. The slightly denser regions eventually, over billions of years, collapsed under gravity to form galaxies, clusters, and the vast cosmic web we see today. Remarkably, the pattern of these ancient fluctuations is imprinted on the cosmic microwave background radiation, the afterglow of the Big Bang, and it matches the predictions of quantum field theory with stunning precision. This means the largest structures in the modern universe, the great walls of galaxies and the immense voids between them, may have their origins in the tiniest, most fleeting quantum whispers at the dawn of time. This incredible connection between the quantum microcosm and the cosmic macrocosm reveals a universe that is deeply, fundamentally interconnected. The same fields that dictate how electrons behave in an atom might also hold the key to the fate of the entire cosmos. It forces us to reconsider what we mean by nothing. Empty space is not an inert stage. It is a vibrant, dynamic medium, teeming with potential and activity, a foundation woven from countless invisible fields whose subtle interactions and fluctuations collectively sculpt the reality we experience, from the smallest particles to the grandest astronomical scales. Now let's dive into one of the most triumphant discoveries in modern physics, a field that doesn't warp spacetime itself, but instead gives substance to the very things that do. This is the Higgs field, and its story begins not with a force but with a fundamental question. Why do things have mass? For a long time, mass was just a property we took for granted. Some particles, like protons and neutrons, are heavy. Others, like photons, are weightless and zip around at the speed of light. But why? What actually gives a particle its mass? The answer, it turns out, isn't found in the particle itself, but in an invisible ocean that fills every corner of the universe. Imagine space is not empty, but is instead filled with a uniform, treacly substance, a cosmic molasses that stretches everywhere. This is the Higgs field. As different fundamental particles move through this field, they interact with it in distinct ways. Particles like photons, the carriers of light, are like Olympic swimmers. They slice through the Higgs field without any resistance whatsoever, which is why they have no mass and travel at the universe's ultimate speed limit. But other particles, like quarks and electrons, are different. They slog through this cosmic molasses. They struggle against it, and that very act of slogging, that resistance to acceleration, is what we experience as their mass. The more a particle interacts with the Higgs field, the heavier it is. This elegant process, known as the Higgs mechanism, is the reason anything has heft at all. Without this field, every fundamental particle would be massless, zipping around at the speed of light. Atoms could never form because electrons wouldn't be captured by nuclei. Stars could never ignite under the pressure of gravity. Chemistry and life as we know it would be impossible. The Higgs field is the silent, unseen architect of structure itself, turning a chaotic soup of energy into a universe of tangible, stable matter. For decades, this was a beautiful but unproven theory. The hunt for its confirmation became one of the greatest scientific quests, culminating in the construction of the most complex machine ever built, the Large Hadron Collider. This 27-kilometer ring buried beneath the Franco-Swiss border is essentially a massive racetrack for particles, smashing protons together at nearly the speed of light to recreate the searing conditions of the early universe. The goal was to find the telltale signature of the Higgs field, a ripple in the field itself which manifests as a particle, the Higgs boson. Think of the field like an ocean. The ocean itself is always there, but if you want to prove the ocean exists, you might look for a splash. The Higgs boson is that splash. Its discovery in 2012 was a monumental event, a thunderous applause from the universe confirming that this invisible field was not just a mathematical abstraction, but a real, physical component of our reality. It was a victory for the very idea that the cosmos is shaped by hidden, pervasive forces. While the Higgs field doesn't directly bend the fabric of space-time like gravity does, its role is no less critical. It operates on a more fundamental level, providing the raw material massive particles that gravity then acts upon. A black hole's immense gravitational pull is a consequence of its enormous mass, and that mass is granted by the Higgs mechanism. In this way, the Higgs field and gravity are partners in a cosmic dance. One provides the substance, and the other sculpts its motion. It's a profound illustration of how these invisible architects don't work in isolation. They are deeply interconnected, each playing its part in a grand, collaborative effort to shape the universe from the most fundamental particles to the largest galactic structures. To understand the cosmos we see today, we must travel back to its very first moments, to a period of almost unimaginable transformation that set the stage for everything to come. The Big Bang Theory gives us a compelling origin story, but it left scientists with some puzzling questions about the present state of the universe. Why is the cosmos so remarkably uniform in every direction we look? The temperature of the ancient light from the Big Bang's afterglow is virtually identical whether we peer east, west, north, or south. This would be like walking into a room where a cup of coffee in one corner and a cup on the opposite side had cooled to the exact same temperature without ever having been in contact. Furthermore, the geometry of the universe appears to be incredibly flat, meaning parallel lines stay parallel, and the rules of Euclidean geometry hold true on the largest scales. According to the original Big Bang model, achieving this level of uniformity and flatness would have required impossibly perfect, fine-tuned initial conditions. It was a cosmic mystery begging for a solution. The answer, known as inflationary theory, is one of the most breathtaking ideas in all of cosmology. It proposes that a fraction of a second after the universe began around 10 to the power of negative 36 seconds. To be vaguely precise, something extraordinary happened. A mysterious high-energy field, now called the inflaton field, temporarily dominated the cosmos. This field possessed a peculiar property. It generated a powerful repulsive gravity, causing the fabric of space-time itself to stretch at an exponential rate that is almost impossible to comprehend. In the tiniest sliver of time, a region of space much smaller than a single proton was blown up to be larger than our entire observable universe today. This wasn't a fast expansion, it was a hyper-explosion of space far exceeding the speed of light. It's crucial to remember that this was an expansion of space itself, not things moving through space, which is why it doesn't violate cosmic speed limits. This incredible growth spurt acted as the ultimate cosmic iron, smoothing out the primordial universe with incredible efficiency. Before inflation, the universe could have been a chaotic, crumpled mess of wildly different temperatures and densities. But by stretching space so abruptly, inflation took any existing wrinkles and stretched them out so they became cosmically vast and incredibly faint, leaving behind a stunningly smooth and uniform expanse. Any major irregularities were literally flattened away, explaining the remarkable uniformity we observe in the cosmic microwave background. It also explains the flatness. Imagine the surface of a partially inflated balloon. It might have all sorts of curves and wrinkles, but if you inflate that balloon to an enormous size, the tiny patch of surface you can see right in front of you appears perfectly flat. Inflation did exactly that to the entire universe, blowing it up so massively that our entire observable cosmos is just a tiny, flat patch on a far grander structure. But inflation did more than just smooth and flatten. It also planted the seeds for all future structure. Due to the quantum fluctuations inherent in all fields, the inflattened field itself was not perfectly uniform. It had tiny, random jitters at the quantum scale. As space expanded exponentially, these microscopic quantum fluctuations were stretched to astronomical sizes. A tiny ripple of extra density here, a slight deficit there, all frozen into the fabric of the now gigantic universe. These minute variations in density became the gravitational seeds for everything that followed. Over the next billions of years, gravity amplified these seeds, pulling slightly denser regions together to eventually form galaxies, stars, and planets. The entire magnificent cosmic web of structure we see mapped across the sky today, the great clusters and vast voids, can trace its lineage back to those infinitesimal quantum whispers magnified by inflation. The most stunning validation of this theory came from incredibly precise maps of the cosmic microwave background, particularly from satellites like the Planck Observatory. These maps reveal a faint, speckled pattern of hot and cold spots, temperature variations of just a few millionths of a degree. This pattern is a literal baby picture of the universe, and its statistical properties match the predictions of inflationary theory with astonishing accuracy. We are essentially seeing the amplified quantum fluctuations of the inflattened field, the primordial blueprint for our universe, frozen in time. Without this brief, violent, and transformative event driven by a single invisible field, our universe would likely be a very different place, perhaps hopelessly lumpy and curved, or even collapsed back in on itself long before stars could ever form. The inflattened field, though transient, was the ultimate primordial sculptor, taking a chaotic, microscopic speck and shaping it into the vast, structured, and habitable cosmos we are privileged to call home. But to truly grasp the universe's deepest mechanics, we must venture beyond the familiar four dimensions of space-time and into a realm where the very notion of a point-like particle dissolves. This brings us to one of the most ambitious and mathematically elegant frameworks in all of physics, string theory. At its heart, string theory proposes a radical shift in perspective. The fundamental building blocks of the universe are not zero-dimensional points, but incredibly tiny, vibrating one-dimensional strings. These strings are unimaginably small, on the order of the Planck length, meaning if an atom were the size of our solar system, a string would be about the size of a tree. And just like a violin string can vibrate at different frequencies to produce distinct musical notes, these fundamental strings vibrate in different modes. It is the unique resonance, the specific vibrational pattern of a string, that determines its properties, whether it manifests as an electron, a quark, a photon, or a graviton. In this symphony of strings, every particle and every force is simply a different note being played on the same cosmic instrument. This elegant idea, however, comes with a breathtaking requirement. The universe must have more than the 3 dimensions of space and one of time that we experience. For the mathematics of string theory to be consistent and to include gravity, it demands extra spatial dimensions. Different versions of the theory require a total of 10, 11, or even 26 dimensions. This immediately raises an obvious and pressing question. If these extra dimensions exist, where are they? Why don't we see them, walk through them, or perceive them in any way? The leading explanation is a process called compactification. Imagine a long, thin garden hose stretching far into the distance. From a great distance, it appears to be a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover an entire second dimension curled up into a tiny circle around the hose's circumference. In much the same way, string theory suggests that at every single point in our familiar 4-dimensional spacetime, there are 6 or 7 additional spatial dimensions, but they are curled up or compactified into an impossibly tiny, complex geometric shape called a Calabi-Yau manifold. These dimensions are so minuscule that they are completely hidden from our everyday perception and even from our most powerful particle colliders so far. The existence of these hidden dimensions isn't just a mathematical curiosity. It could be the key to solving some of the most persistent puzzles in physics. Take, for example, the shocking weakness of gravity. Gravity is vastly weaker than the other fundamental forces. A small refrigerator magnet can generate enough electromagnetic force to overcome the entire gravitational pull of the Earth and stick to the door. Why is there such a staggering difference in strength? String theory offers a compelling visual analogy. Imagine our 4-dimensional universe is a vast 2-dimensional membrane, or brain, floating within a higher dimensional space. The particles of the standard model, like electrons and quarks, are like ink droplets trapped on the surface of this membrane, unable to leave it. But the graviton, the hypothetical particle that carries the gravitational force, is a closed loop of string. Unlike the other particles, it is not attached to our brain and is free to propagate into the full bulk of the higher dimensions. In this scenario, gravity's strength appears diluted to us because its force lines are not confined to our 3-dimensional space. They are spreading out or leaking into these extra dimensions. What we perceive as weakness is actually a signal of gravity's freedom to explore the full geometric architecture of reality. This concept of a multidimensional cosmos also provides fertile ground for explaining dark matter. Could dark matter be ordinary matter, perhaps even entire stars and galaxies that exists on a separate, parallel brane very close to our own? If so, we would be completely blind to its light, but we would still feel its gravitational influence, as gravity, again, can travel between branes. It's a speculative idea, but it showcases how thinking in higher dimensions radically expands the toolkit of the cosmic sculptors. The shapes of these extra dimensions, the precise geometry of the curled-up Calabi-Yau spaces, would directly determine the properties of the particles and forces we observe. The mass of an electron, the strength of the electromagnetic force, even the number of generations of particles, could all be dictated by the topology of these unseen dimensions. In this framework, the ultimate sculptors of reality are not just fields, but the very geometry of the universe's hidden architecture. The laws of physics themselves may be a direct consequence of how these extra dimensions are folded and woven into the fabric of existence, a silent, geometric symphony that dictates every note played in the cosmic opera we call reality. This constant, simmering activity of the quantum vacuum isn't just a theoretical curiosity. It has a name and a profound physical implication. It's called vacuum energy, and it represents a background hum of energy that is woven into the very fabric of what we call empty space. According to the principles of quantum field theory, this energy should be everywhere, a permanent and pervasive feature of the cosmos, exerting a constant pressure on the fabric of space-time itself. This is where the story takes a fascinating and deeply puzzling turn, connecting the frantic activity of the quantum world to the grandest scales of the universe. The cosmological constant, that term Einstein introduced and later discarded, was resurrected with the discovery of the universe's accelerating expansion. It is the simplest possible explanation for dark energy, a constant energy density inherent to the vacuum of space. In this view, vacuum energy is the cosmological constant. As the universe expands and new space is created, more of this vacuum energy comes into existence, generating the repulsive force that drives galaxies apart faster and faster. It's an elegant idea, beautifully linking the physics of the very small to the fate of the very large. Yet this elegant idea is shattered by one of the most glaring discrepancies in all of modern science, a problem so severe it has been called the worst theoretical prediction in the history of physics. When physicists attempt to calculate the expected value of this vacuum energy using our well-tested theories of quantum mechanics, they run the numbers and get an answer. But this answer is mind-bogglingly, incomprehensibly large. We're talking about a value that is 10 followed by 120 zeros times stronger than the value we actually observe from astronomical measurements of the universe's expansion. To put that in perspective, it's the difference between the energy contained in a single gallon of gasoline and the energy of all the oceans on Earth. If the quantum field theory calculation were correct, the vacuum energy would have been so unimaginably powerful in the first instance after the Big Bang that it would have instantly blown any potential for structure atoms, stars, us into oblivion before it could even begin to form. The fact that we exist to ponder this question means the actual, observed value of the vacuum energy is not just a little off, it is infinitesimally small, fine-tuned to a degree that defies all logic and probability. This yawning chasm between theory and observation is the infamous cosmological constant problem, and it represents a fundamental crisis in our understanding. It screams that we are missing something absolutely crucial, that our grasp of how quantum fields behave in the context of gravity and curved spacetime is woefully incomplete. Perhaps the contributions from the countless fluctuating fields somehow cancel each other out almost perfectly, leaving behind only a tiny, residual effect through some unknown, supersymmetric mechanism. Or perhaps the vacuum energy is not a constant at all, but a dynamic field that has decayed or evolved over the life of the universe from that immense initial value down to the faint whisper we detect today. Another, more radical possibility is that we are entirely wrong about the source of the acceleration, and that it points not to an energy in the vacuum, but to a need to modify our theory of gravity itself on the largest scales, a breakdown of Einstein's general relativity that would require a new revolutionary framework. Regardless of its ultimate resolution, the concept of vacuum energy perfectly embodies the subtle, persistent, and enigmatic influence of invisible fields. It is a ghost in the cosmic machine, a signature of the quantum world etched onto the canvas of the entire universe. Its predicted strength reveals the raw, unharnessed power thrumming within emptiness, while its observed gentleness is one of the greatest mysteries we have ever encountered. Unlocking this puzzle may require nothing less than a complete unification of quantum mechanics and gravity, a theory of everything that would finally reveal how these invisible sculptors work in concert, from the quantum foam to the expanding cosmos, to carve the stable and habitable reality we experience. For centuries, our study of the cosmos relied entirely on light. We built telescopes to collect photons, those tiny messengers traveling across the void, to paint a picture of the universe. But light can be blocked, distorted, or simply never emitted from the most dramatic events in space. It was like trying to understand a storm by only watching the lightning, completely deaf to the thunder. Then, in 2015, a new sense opened up. For the first time, we didn't just see the universe, we felt it. We felt a literal ripple in the fabric of reality pass through the Earth itself, a vibration so minuscule it required perhaps the most precise measurement in human history to detect. This was the first direct observation of gravitational waves, and it confirmed a prediction Einstein made a century earlier in the most spectacular way possible. So what exactly are these ripples? Remember our analogy of spacetime as a flexible rubber sheet. When objects move gently across this sheet, like a planet orbiting a star, they create gentle, continuous warps. But if you take two incredibly massive objects like black holes and have them orbit each other at a significant fraction of the speed of light, they don't just bend the sheet, they violently churn it. Their insane acceleration sends powerful waves radiating outward through the fabric of spacetime itself, much like a boat speeding across a lake creates a wake, or two children spinning each other around on a trampoline would send vibrations across its surface. These are gravitational waves. They are not waves in space. They are waves of space, compressing and stretching the very distances between points as they pass through. The effect is unimaginably small. A typical wave passing through Earth might change the distance between you and a friend by less than the width of a single proton. Detecting such a tiny signal required an instrument of almost unbelievable sensitivity, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Each LIGO observatory consists of two 4-kilometer long arms arranged in an L shape. Inside these vacuum tubes, a powerful laser beam is split and sent racing down each arm, bouncing off perfectly polished mirrors at the end to travel back and recombine. If no gravitational wave passes through, the light waves return and cancel each other out perfectly. But if a ripple from a distant cosmic catastrophe stretches one arm while compressing the other, even by 1,000th the width of a proton, the laser light traveling down them is affected differently. They return out of sync, and instead of cancelling out, they create a flicker of light, a signal. To ensure these detections aren't just local noise like a distant truck rumbling by, two identical detectors, one in Louisiana and one in Washington state, must see the same signal within milliseconds of each other. The first signal ever detected, named GW150914, was a textbook-perfect example. It was the death spiral of two black holes, one about 36 times the mass of our Sun, the other 29, locked in a final, furious dance over 1 billion light-years away. The signal, when converted to sound, is a haunting chirp, a rapid rise in frequency and amplitude as the black holes orbit faster and faster, closer and closer, until they finally merge into a single, more massive black hole in a cataclysm that, for a brief moment, released more power than all the stars in the observable universe combined. The energy radiated away in those gravitational waves was in the form of pure space-time curvature. Since that historic first detection, LIGO and its European counterpart, Virgo, have listened to dozens of these cosmic events, more black hole mergers, and also the collisions of ultra-dense neutron stars, which flash with light and heavy elements like gold and platinum, allowing us to both hear and see the same event. This new window on the universe does more than just confirm spectacular collisions. It lets us test the very laws of physics in the most extreme environments imaginable. By analyzing the precise shape of these gravitational wave signals, scientists can probe the nature of gravity itself. Do the waves behave exactly as Einstein's theory predicts near these incredible densities, or do they show subtle deviations that might point toward new physics, perhaps even hints of those elusive quantum gravity effects? Furthermore, these ripples can act as a new tool for mapping the influence of the invisible sculptors. If a gravitational wave passes through a region dense with dark matter, for instance, its properties might be subtly altered, giving us a novel way to detect and measure this mysterious substance. Each chirp from the dark is like an echo from the sculptor's workshop, carrying encoded information not just about the objects that created it, but about the properties of the space-time they traveled through and the hidden fields that may permeate it. We are no longer just astronomers, we have become cosmic cartographers, using the vibrations of space-time to chart a universe that was previously silent and hidden from our view. If gravity is the artist and dark matter the framework, then black holes are the universe's most extreme and violent workshops, places where the very rules of physics are pushed to their absolute breaking point. These cosmic phenomena are not just objects in space, they are regions where space-time itself undergoes a catastrophic failure, a breakdown in geometry so complete that our current understanding simply cannot follow. At the heart of a black hole lies the singularity, a point of theoretically infinite density where the curvature of space-time becomes infinite and the known laws of physics cease to function. This is surrounded by the event horizon, a spherical boundary that marks the point of no return. Think of it not as a physical surface, but as a one-way door in the fabric of the cosmos. Anything that crosses this threshold, whether a speck of dust, a planet, or a beam of light, is irrevocably lost to our universe, its entire future now dictated by the unimaginable pull of the singularity. The effects of this extreme warping are almost beyond comprehension. As you approach a black hole, the gravitational forces become so intense that they create a phenomenal difference in pull between your head and your feet, a process physicists call spaghettification, stretching any object into a long, thin stream of atoms. The distortion of time is even more mind-bending. Due to the incredible gravity, time itself slows down dramatically relative to a distant observer. Imagine a spacecraft on a mission to orbit a black hole. To the crew on board, time might feel like it's passing normally, but for everyone back on Earth watching from a safe distance, the clocks on that ship would appear to tick slower and slower. If the ship were to hover just outside the event horizon, its crew could witness the entire future evolution of the universe flash before them in what felt like moments, while billions of years passed for everyone else. Light, too, is not immune. It bends around the black hole in such extreme ways that if you were able to safely orbit one, you would be able to see the back of your own head, as light would wrap all the way around the black hole and come back to your eyes. For decades, these were predictions on paper, the stunning but unproven consequences of Einstein's equations. That changed in April 2019, when the Event Horizon Telescope collaboration unveiled the first ever direct image of a black hole. This was not a photograph in the traditional sense, but a reconstructed image made from data collected by a global network of radio telescopes synchronized to act as one Earth-sized instrument. The target was a supermassive black hole at the heart of the galaxy Messier 87, a behemoth with a mass 6.5 billion times that of our Sun. The image showed exactly what Einstein's theory predicted: a dark central shadow, which is the event horizon itself, silhouetted against a brilliant, asymmetric ring of superheated gas swirling at near light speed. This glowing ring is the light from that accretion disk, being bent and lensed by the black hole's immense gravity in a perfect demonstration of extreme gravitational lensing. This monumental achievement did more than just provide a spectacular picture. It was a powerful validation of general relativity operating in the most extreme environment imaginable. Yet, for all that general relativity explains about the outsized power of black holes, it creates a profound paradox when it meets the other pillar of modern physics, quantum mechanics. This is the infamous black hole information paradox. Quantum mechanics states that information about a physical system, the properties of every particle that falls into the black hole, can never be truly destroyed. But general relativity, with its ruthless event horizon and point-like singularity, seems to demand that all that information is irretrievably lost, erased from our universe. This contradiction suggests that our theories are incomplete. Resolving it is the holy grail of theoretical physics, pushing scientists toward a theory of quantum gravity. One of the most fascinating ideas to emerge from this struggle is the holographic principle, which suggests that all the information describing everything that ever fell into a three-dimensional black hole might actually be encoded on its two-dimensional event horizon, like a cosmic fingerprint. In this view, the black hole's surface acts as a hologram, storing a perfect record of its contents, and the three-dimensional interior we imagine might be a kind of illusion projected from that data-rich boundary. This makes black holes far more than just cosmic vacuum cleaners. They are the ultimate natural laboratories, the most violent and extreme environments where the deepest secrets of reality are forged. They are the testing grounds where our ideas about space-time, information, and the fundamental forces are stretched to the limit and often broken. By studying them, we are not just learning about the death of stars, we are peering into the very heart of the mystery, seeking to understand how the invisible sculptors of space-time behave when the fabric of reality is twisted into a knot. They challenge us to find a deeper, more complete theory of everything, one that can finally reconcile the immense and the infinitesimal. But if black holes are the universe's ultimate paradox, then the holographic principle might be the key to unlocking it, offering a perspective so radical it challenges our most basic assumptions about reality. This mind-bending idea suggests that our experience of a rich, three-dimensional universe might be a kind of magnificent illusion, a projection from a two-dimensional surface, much like the seemingly three-dimensional image encoded on the flat surface of a credit card hologram. The seeds of this concept were planted by the black hole information paradox itself. When physicists like Jacob Bekenstein and Stephen Hawking studied black holes, they made a startling discovery. The maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it's proportional to the area of its event horizon, its two-dimensional surface. It was as if the entire three-dimensional interior of the black hole was being described by bits of information painted on its outer shell. This revelation led theorists to a breathtaking leap. Perhaps this isn't just a quirky property of black holes. Maybe it's a fundamental law of the universe. The holographic principle proposes that all the information needed to describe everything within any given volume of space, every star, every planet, every person, every atom, could be entirely encoded on the boundary of that volume. In this view, the three-dimensional world we see and move through is not the fundamental reality. It is emergent, a holographic projection from a vast, complex network of information stored on a distant, two-dimensional surface that surrounds us. We are, in a very real sense, living inside a cosmic hologram. To grasp this, consider a more familiar example, a three-dimensional video game. The breathtakingly detailed world you explore on your screen isn't actually stored in your computer as a miniature three-dimensional universe. It is encoded on a two-dimensional hard drive as a series of ones and zeros pure information. The processor reads this data and projects it into the rich, interactive, three-dimensional experience you see. The holographic principle suggests the universe operates on a similar, though infinitely more complex, principle. The fundamental ingredients of reality may not be particles or fields in space, but bits of information. Space-time itself, with its three dimensions of space and one of time, may not be the foundation but a secondary structure that emerges from the intricate quantum entanglement of these informational bits on a lower dimensional surface. This idea finds a concrete mathematical home within string theory, in a concept known as the AD-S/CFT correspondence. This is a powerful duality, a theoretical dictionary that translates problems in a hypothetical universe with a certain type of curvature and gravity, a bulk, into equivalent problems in a quantum field theory without gravity that exists on its boundary. A calculation about the difficult behavior of black holes in the three-dimensional bulk can be translated into a more manageable calculation about particles and fields on the two-dimensional boundary, and vice versa. This correspondence provides a working, mathematical model of the holographic principle, strongly suggesting that gravity and the dimensionality of our world are not fundamental, but are emergent phenomena arising from a quantum system that operates on a completely different plane. If this is true, it completely reimagines our search for the sculptors of spacetime. The primary architects of reality would no longer be the quantum fields we've been discussing, vibrating within space. Instead, they would be these more fundamental, informational degrees of freedom, perhaps a vast, entangled quantum state residing on a lower dimensional surface we cannot perceive. The forces and particles we experience, including gravity itself, would be akin to shadows cast by the dynamic interactions happening on this distant, foundational screen. The bending of spacetime by a planet, the acceleration of the universe's expansion, the very fabric of reality itself, would all be a grand and spectacular projection. This principle doesn't diminish the wonder of the cosmos. It deepens it, suggesting that the true masterpiece is the hidden code, and the magnificent, four-dimensional universe we inhabit is its most beautiful and immersive rendering. For all their breathtaking success, our two most powerful theories of reality are locked in a fundamental and seemingly irreconcilable conflict. On one hand, we have general relativity, which masterfully describes the universe on its largest scales, the graceful dance of galaxies, the curvature of spacetime around stars, and the awesome power of black holes. It paints a picture of a smooth, continuous, and flexible fabric. On the other hand, we have quantum mechanics, which with stunning accuracy governs the bizarre world of the very small, the probabilistic behavior of particles, the entanglement of states across vast distances, and the frenetic energy of the quantum vacuum. This theory reveals a universe that is granular, fuzzy, and discontinuous. For nearly a century, these two titans have operated in separate domains, each ignoring the other's existence. But this peaceful coexistence shatters at the extremes, in places where immense gravity meets microscopic scale, at the center of a black hole, or the very first moment of the Big Bang. Here, the equations of both theories break down, producing nonsensical answers like infinities, screaming that our understanding is incomplete. Unifying them into a single, coherent framework is the single greatest outstanding challenge in fundamental physics, a quest known as the search for a theory of quantum gravity. The core of the conflict is a clash of philosophies. General relativity is a classical theory. It is deterministic and local. If you know the state of a system and the curvature of spacetime, you can perfectly predict its future motion. Quantum mechanics, however, is inherently probabilistic and non-local. You can only speak of the probability of finding a particle in a certain place, and particles can influence each other instantaneously across space, a phenomenon that deeply troubled even Einstein, who called it spooky action at a distance. Trying to force these two contradictory worldviews to merge is like trying to mix oil and water. When physicists attempt to describe gravity using the same quantum field theory techniques that work so perfectly for the other three forces, the mathematics explodes into a mess of infinities that cannot be tamed. This tells us that a more radical, deeper theory is required, one that doesn't just combine the existing pieces, but rewrites the rules from the ground up. Several ambitious paths are being explored in this grand quest. String theory, as we've discussed, proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings, and that gravity emerges naturally from their oscillations in a higher dimensional space. Another compelling contender is loop quantum gravity. This approach takes the lessons of quantum mechanics and applies them directly to the fabric of space-time itself. Instead of a smooth continuum, it proposes that space is not infinitely divisible. It is woven from a network of tiny, discrete, one-dimensional loops, forming a structure often called a spin network. Picture the fabric of reality not as a smooth sheet, but as an incredibly fine mesh, with the smallest possible unit of area being a single cell in this mesh, on the order of the Planck area. Time, too, may be granular, advancing not as a continuous flow but in the tiniest possible increments, like the individual frames of a cosmic movie. In this view, the Big Bang might not have been a singularity of infinite density, but a big bounce, a moment where a previous universe collapsed and then rebounded due to these quantum properties of space. At this unimaginably small scale, the Planck scale, the very concepts of location and distance break down. The vacuum of space is not peaceful. It is a chaotic, foaming sea of quantum fluctuations where spacetime itself is believed to churn with violent turbulence. This is the domain where the invisible sculptors we've been discussing would operate in their most fundamental form. In the frameworks of these theories, the fields that give rise to particles and forces might also be the very substance from which spacetime itself is woven. Their interactions and entanglements could be what gives rise to the geometry we experience as the four-dimensional universe. The goal of quantum gravity is to find the mathematical language that describes this primordial chaos, to show how the smooth, classical spacetime of general relativity emerges from this seething quantum underpinning, much like the calm surface of a lake emerges from the frantic motion of countless water molecules. Resolving this divide is not an academic exercise. It is crucial for answering the most profound questions about our existence. Without a theory of quantum gravity, we cannot understand the true nature of the Big Bang, what, if anything, came before it, or how something can emerge from nothing. We cannot peer beyond the event horizon of a black hole to understand the fate of information and the singularity at its core. Most importantly for our journey, we cannot finally identify the ultimate sculptors of spacetime. Are they vibrating strings, loops of quantum geometry, or something even more exotic? Discovering the theory that bridges this century-old divide will be one of the crowning achievements of human intellect, finally revealing how the universe constructs reality itself from its most basic, invisible ingredients. Now we arrive at one of the most profound and embarrassing problems in all of modern physics. A discrepancy so vast it has been called the worst prediction in the history of science. It's known as the cosmological constant problem, and it reveals a shocking gap in our understanding of how the quantum world connects to the cosmos. Remember that seething quantum foam, the vacuum energy generated by particles flickering in and out of existence. When physicists use their incredibly successful equations of quantum field theory to calculate the strength of this energy, they get a number. But this number is not just a little bit off, it is catastrophically, unimaginably wrong. The calculated value is 10 followed by 120 zeros times larger than the value we actually observe for the dark energy accelerating the expansion of the universe. To put that in perspective, it's the difference between the energy contained in a single drop of water and the energy of all the oceans on every planet in the entire observable universe. If the quantum field theory calculation were correct, the repulsive force of this vacuum energy would have been so immense that it would have ripped the infant universe apart in the first fraction of a second, preventing any galaxy, star, or planet from ever forming. The fact that we exist to measure this energy means the actual value is not just small, it is infinitesimal, fine-tuned to a degree that defies all reasonable explanation. This isn't a minor accounting error, it's a screaming void in our knowledge, indicating that something is missing from our equations. The leading suspicion is that there must be some unknown mechanism, some hidden symmetry or dynamic field, that cancels out almost all of this vacuum energy with near-perfect precision, leaving behind only the tiny, residual effect we detect as dark energy. It's as if two cosmic titans are engaged in a fierce tug of war, their immense forces perfectly balanced to within a hair's breadth, resulting in the gentle, barely perceptible push we observe. The problem is, we have no idea what these titans are or what rules govern their struggle. This fine-tuning is so exquisite that it borders on the miraculous, forcing physicists to consider possibilities that range from the revolutionary to the philosophical. One provocative explanation is the Anthropic Principle. This idea suggests that the cosmological constant has the value it does because if it were any different, we wouldn't be here to observe it. In a multiverse of countless universes, each with different physical constants and random values for their vacuum energy, only those rare universes with an incredibly small cosmological constant would be calm and stable enough to allow for the formation of galaxies, stars, planets, and ultimately, life. We find ourselves in such a universe not because of any fundamental law, but simply by selection bias. A universe with different parameters would be barren and empty, with no one to ponder its laws. While this idea offers a potential explanation, it is deeply unsatisfying to many scientists because it moves the question from physics to metaphysics, essentially stating that the value is what it is because we are here to see it. Other theories propose more dynamic solutions. Perhaps dark energy is not a true constant after all, but a field that has evolved over time. This concept, sometimes called quintessence, suggests a cosmic field that was once much stronger but has since decayed or diluted to its present faint state. Another possibility is that we are fundamentally misunderstanding how quantum field theory operates in the context of curved spacetime and gravity. Our calculations assume a flat, static background for the quantum fields to play out on, but in the real, dynamic, and expanding universe, this might be a fatal oversimplification. The true resolution will likely require a full theory of quantum gravity, a framework that seamlessly blends the physics of the very small with the physics of the very large, something that has eluded us for a century. The cosmological constant problem is more than just a technical puzzle. It is a profound reminder of our place in the cosmos. It highlights the incredible, seemingly improbable balance of the fundamental forces and constants that allow for our existence. The invisible fields that sculpt our reality must be exquisitely tuned, their parameters set within an impossibly narrow range to carve out a universe that is not only stable but also habitable. This fine-tuning suggests that either there is a deeper, more beautiful layer of physical law waiting to be discovered, a symmetry or principle that naturally explains this balance, or we must accept that our universe is a rare and precious oasis in a much wider and stranger metacosmos. Either way, the problem stands as a monument to our ignorance, a beacon urging us to look deeper and question further. But what if we've been looking at the entire problem from the wrong angle? The prevailing model of cosmology relies on two mysterious, invisible components, dark matter and dark energy, to explain the universe's behavior. But an intriguing alternative asks a radical question. Could it be that we don't need to invent new, unseen substances? What if, instead, our understanding of gravity itself is incomplete? This is the bold proposition of modified gravity theories, a fascinating branch of physics that suggests we might not need dark matter or dark energy at all if we're willing to tweak the rules laid down by Einstein himself over a century ago. The most prominent of these alternatives is a theory known as MUND, which stands for Modified Newtonian Dynamics, proposed by physicist Mordechai Milgrom in the early 1980s. MUND starts from a simple but powerful observation. The need for dark matter only arises in environments where gravity is exceptionally weak, like the outer edges of galaxies where stars orbit at surprisingly high speeds. Milgrom suggested that instead of invoking an invisible halo of matter to provide extra gravitational glue, perhaps Newton's law of gravity, and by extension, Einstein's, deviates from its usual behavior in these extremely low acceleration environments. In simple terms, MUND proposes that gravity doesn't weaken with distance quite as sharply as our standard equations predict. In the faint, sprawling outskirts of a galaxy, gravity might get a subtle second wind, providing just enough extra pull to keep those fast-moving stars from flying away, all without any dark matter required. To its credit, MUND is surprisingly successful at explaining the rotation curves of a wide variety of galaxies with a single new constant, something the dark matter model often struggles with without adding numerous extra parameters. However, MUND, in its original form, is not a complete relativistic theory. It doesn't seamlessly incorporate into the framework of spacetime curvature. This has spurred the development of more sophisticated theories that attempt to modify gravity in a way that is consistent with Einstein's broader picture. These are known as scalar tensor theories. In general relativity, gravity is mediated by the geometry of spacetime, the curvature of the fabric. Scalar tensor theories introduce an additional element, a new field that permeates space, often called a scalar field because it has magnitude but no direction. This field interacts with gravity, effectively changing its strength depending on the environment. It's as if the stiffness of the cosmic rubber sheet isn't a fixed property but can vary from place to place, altering how deeply objects warp it and how other objects roll along its curves. These theories don't just offer an alternative to dark matter. Some also aim to explain the accelerated expansion of the universe without dark energy. By carefully designing how this new scalar field evolves over cosmic time, theorists can make it produce a repulsive force that kicks in on the larger scales, mimicking the effect of dark energy and driving galaxies apart. This creates a more unified picture where a single modification to gravity could potentially account for two of the biggest mysteries in modern cosmology. The appeal is undeniable, a universe where the strange behavior we see is due to a deeper law of gravity rather than a cosmos dominated by substances we cannot directly detect. Yet, these theories face significant challenges. While they excel at explaining the behavior of individual galaxies, they have a much harder time accounting for all the evidence we have for dark matter's gravitational influence on larger scales. Observations of colliding galaxy clusters like the famous Bullet Cluster provide a particularly tough test. In these collisions, the vast clouds of hot gas, the normal, visible matter, slams into each other and slows down. But the gravitational lensing effect, which maps the total mass, shows that most of the mass has sailed right through the collision, completely separate from the gas. This is exactly what you would expect if the mass were made of collisionless dark matter particles, but it's very difficult for a modified gravity theory to explain how gravity itself could become disconnected from the visible matter and found in a different location. This ongoing tension is actually the lifeblood of scientific progress. The fact that modified gravity theories exist and are actively pursued is incredibly healthy for cosmology. They act as a necessary counterweight, constantly challenging the standard model and forcing its proponents to sharpen their arguments and seek even more definitive evidence. They remind us that our models are just that, models. They are approximations of reality, and sometimes a revolutionary adjustment to a foundational law can be more elegant than populating the universe with invisible entities. Whether these alternative theories ultimately prove to be correct is less important than the role they play in expanding our imagination. They boldly assert that the rules of reality might be more flexible and surprising than we currently imagine, encouraging us to consider that the true sculptors of spacetime might not be hidden substances, but hidden nuances in the force of gravity itself. But to truly appreciate the intricate choreography of these invisible fields, we must understand the silent conductor guiding their every move: symmetry. This isn't about mere visual balance. In physics, symmetry is a profound and powerful principle that dictates the very rules of the game, determining which interactions are allowed and which laws are inviolable. At its core, a symmetry in nature means that a situation remains unchanged or invariant, even after undergoing a specific transformation. A simple example is a perfect, featureless sphere. You can rotate it any way you like, and it looks exactly the same. The sphere is symmetric under rotation. In the early 20th century, mathematician Emmy Noether made a breathtaking discovery that forever linked these abstract symmetries to tangible physical laws. She proved that for every continuous symmetry in nature, there is a corresponding conservation law. This profound connection, known as Noether's theorem, reveals that the deepest principles of our universe are rooted in symmetry. The fact that the laws of physics are the same at every point in space, a symmetry known as translational invariance, directly leads to the conservation of momentum. The fact that these laws are the same in every direction leads to the conservation of angular momentum, and the fact that they are the same at every moment in time leads to the conservation of energy. These aren't just separate, lucky coincidences. They are the inevitable consequences of a symmetric cosmos. The very predictability of the universe, the fact that we can run experiments today and trust they will yield the same results tomorrow, is a gift of this underlying temporal symmetry. This concept of symmetry extends even further into the fabric of reality through a special class known as gauge symmetries. These are more abstract, relating not to motions in space and time, but to internal properties of fields and particles. Imagine a field like the electromagnetic field, described by a value at every point in space. A gauge symmetry means that we can change or recalibrate that value in a specific way at every point, and yet all the observable physics, the forces we measure, the light we see, remains completely unchanged. It might sound like a mathematical curiosity, but this requirement of local gauge invariance is actually what demands the existence of force-carrying particles. To allow the electromagnetic field to have this local symmetry, nature must introduce a messenger particle, the photon to mediate the force and ensure everything stays consistent. In this way, the symmetry doesn't just describe a force, it actually dictates its existence. The entire standard model of particle physics is built upon this powerful framework of gauge symmetries. The strong nuclear force that binds quarks together inside protons and neutrons, and the weak nuclear force responsible for radioactive decay, each arise from their own specific gauge symmetries. These invisible mathematical principles act as the ultimate architects, constraining the possible ways fields can interact and ensuring the universe operates with a consistent and elegant set of rules. Yet, if the universe were perfectly symmetric in all ways, it would also be profoundly boring. A cosmos with unbroken symmetry would contain a bland, uniform soup of massless particles and undifferentiated forces. The breathtaking diversity we see, the different masses of particles, the distinct strengths of forces, the very structure of atoms arises from a process beautifully known as spontaneous symmetry breaking. Think of a pencil balanced perfectly on its sharp tip. This state has a high degree of rotational symmetry. It looks the same from every direction, but it is also incredibly unstable. The slightest disturbance will cause it to fall over and point in one specific, random direction. The symmetry of the system is now broken. It has chosen a preferred axis, and the perfect rotational symmetry is hidden. However, the underlying laws that describe the pencil are still symmetric. It's just the settled state that appears asymmetric. This is precisely what happens in the Higgs field. The equations describing the field are perfectly symmetric, but the lowest energy state of the universe, the vacuum we live in, is not. The Higgs field has settled into a non-zero value everywhere, much like the pencil choosing a direction to fall. This breaking of the electroweak symmetry is what gives mass to the W and Z bosons, differentiating the weak nuclear force from electromagnetism and allowing particles like electrons and quarks to acquire their mass through the Higgs mechanism. The diversity of the particle zoo, and indeed the possibility of structure itself, is a direct result of this broken symmetry. These principles of symmetry and its breaking are the invisible guides that constrain how all fields, from the gravitational to the Higgs, can sculpt space-time and influence phenomena. They are the reason the cosmos is not a chaotic free-for-all but a realm of stunning order and predictability. The conservation laws that govern the motion of planets, the fundamental forces that dictate the behavior of atoms, and the very mass that allows matter to clump into galaxies, all of these are orchestrated by the deep, often hidden, symmetries of nature. Appreciating this role allows us to see the universe not as a collection of disparate rules, but as a unified and elegant tapestry, woven from a few simple symmetric principles whose careful breaking gave rise to the rich and complex reality we are part of today. Now let's venture into what might be the strangest and most profound connection of all, a concept that seems pulled from the pages of science fiction, but is grounded in serious theoretical physics. This is the mysterious link between quantum entanglement and the very fabric of space-time. You've likely heard of entanglement, often called spooky action at a distance by Einstein. It describes a situation where two particles become deeply linked, their fates intertwined no matter how far apart they travel. Measure the property of one like its spin or polarization, and you instantly know the state of its partner, even if that partner is on the other side of the galaxy. This isn't just a prediction, it's been confirmed in laboratories time and again, and it completely upends our classical, intuitive notion of how information can travel. It challenges the principle of locality, the idea that objects are only influenced by their immediate surroundings. Entanglement suggests a deeper, invisible connection that operates outside the bounds of space and time as we understand them. For decades, physicists treated quantum mechanics and general relativity as two separate kingdoms, one ruling the tiny quantum world and the other governing the grand cosmic arena. Entanglement was a quirky feature of the quantum realm, and space-time curvature was the domain of gravity. They were seen as unrelated, but a revolutionary idea is now bridging this divide, suggesting that these two bizarre phenomena might not just be connected, they might be two sides of the same coin. This bold proposal is known as the ER equals EPR conjecture. It was put forward by physicists Juan Maldacena and Leonard Susskind, and it proposes a stunning duality. ER refers to Einstein-Rosen bridges, which is the formal term for wormholes, theoretical tunnels in spacetime that could connect distant points. EPR refers to Einstein, Podolsky, and Rosen, the authors of the famous paper that first highlighted the paradox of entanglement. The conjecture suggests that when two particles are entangled, they aren't just mysteriously linked, they are, in fact, connected by a microscopic wormhole. This isn't a wormhole you could travel through, it's unimaginably tiny, existing at the Planck scale, but the implication is staggering. It posits that the spooky, instantaneous connection of entanglement is actually mediated by a geometric structure in spacetime itself. The wormhole provides a physical bridge, making the connection less like magic and more like a hidden piece of plumbing in the universe's infrastructure. In this view, every pair of entangled particles is joined by an invisible thread of warped spacetime, weaving a complex web of connections that underlies reality. This leads to an even more radical possibility. If entanglement can create these tiny wormholes, could it be that all of spacetime is woven together by a vast network of quantum entanglement? Perhaps spacetime itself doesn't exist as a fundamental entity. Maybe what we perceive as the smooth, continuous fabric of the universe is actually emergent, a geometric projection that arises from an underlying quantum system of incredibly complex, entangled connections. Think of a three-dimensional hologram that emerges from a two-dimensional surface encoded with information. In a similar way, our four-dimensional universe of space and time might emerge from a lower-dimensional quantum system where the primary ingredients are not points and lines, but entangled quantum bits or qubits. The distance between two objects in space might not be a fundamental property, but rather a measure of how deeply entangled they are. Less entanglement could mean greater perceived distance, while deep entanglement could create the geometric equivalent of a shortcut through the cosmos. This perspective turns our traditional understanding inside out. We usually think of entanglement as something that happens within spacetime, but this new idea suggests that spacetime itself is built from entanglement. The gravitational force that bends the paths of planets and light might be a manifestation of the need to maintain these quantum connections across the universe. This research is rapidly blurring the line between quantum information science and gravitation, creating a vibrant new field at their intersection. It positions quantum entanglement not as a curious side effect, but as a potential fundamental sculptor of reality. It could be the invisible loom weaving the cosmic tapestry, using threads of information and connection to generate the geometry of everything we see and feel. This isn't just about explaining a weird quantum effect. It's about uncovering the very source code of the universe, suggesting that the ultimate architects of spacetime are the profound, non-local bonds that tie one quantum state to another across the vast expanses of creation. This idea of a multiverse pushes the very boundaries of what we consider reality, suggesting that our entire cosmos, with its hundreds of billions of galaxies, might be just a single bubble in a vast, frothing cosmic ocean. The concept emerges naturally from one of our most successful cosmological theories, inflation. we've discussed how a primordial inflattened field likely drove a period of hyper-expansion, smoothing and flattening our observable universe. But what if that process never truly stopped? The theory of eternal inflation proposes that this explosive expansion is still happening somewhere, right now. Imagine a boiling pot of water with bubbles constantly forming and rising to the surface. In this metaphor, the boiling water is the high-energy inflattened field, and each steam bubble is an entire new universe, pinching off and expanding into its own separate reality, with its own distinct laws of physics. In this eternal froth, the process is endless, generating an infinite number of these bubble universes, collectively constituting the multiverse. Within each of these isolated bubbles, the conditions could be radically different from our own. This is where the invisible sculptors we've been exploring take on a meta-cosmic role. As each new universe forms and cools, the various fields that govern physics, the Higgs field, the fields for the nuclear forces, and the field responsible for dark energy, could settle into different states like a cosmic dice landing on a new set of numbers every time. In one universe, the Higgs field might be stronger, giving all particles so much mass that they instantly collapse into black holes. In another, the electromagnetic force might be too weak to allow atoms to form. The strength of gravity, the number of spatial dimensions, even the types of fundamental particles could all be determined by the random, frozen configuration of these fields at the birth of each bubble. Some universes might be stillborn, collapsing immediately or expanding into barren, empty voids. Others might be wildly exotic, filled with forms of matter and energy we cannot even conceive. This provides a powerful, if speculative, answer to one of the most perplexing questions in modern science. Why is our universe so perfectly fine-tuned for life? The fundamental constants of nature appear to be exquisitely balanced on a knife's edge. If the force of gravity were even slightly stronger, stars would burn out too quickly for life to evolve. If the weak nuclear force were even marginally weaker, hydrogen would never fuse into helium, and no stars would shine at all. For decades, this incredible fine-tuning seemed to demand an explanation, often invoked as evidence for a divine creator. The multiverse hypothesis offers a purely naturalistic alternative, the Anthropic Principle. We should not be surprised to find ourselves in a universe with the right conditions for life, because in an infinite ensemble of universes with all possible physical laws, we could only ever arise in one of the extremely rare habitable ones. Our existence is a form of selection bias. We are not witnessing a universe designed for us. We are simply the lucky winners of a cosmic lottery, living in a bubble where the invisible sculptors happen to carve a reality that allows for galaxies, planets, and conscious beings to ponder their own origins. While this idea is currently untestable in any direct way, as these other universes would be forever beyond our observational horizon, it profoundly expands the scope of our quest. It implies that the fields we are trying to understand are not just local actors on the stage of our single universe. They might be fundamental components of a much larger meta-reality, with their values and interactions varying across an unimaginably vast landscape of possibilities. The search for a unified theory of everything then becomes not just about finding the equations that govern our cosmos, but about understanding the overarching rules that dictate the entire menu of possible universes the multiverse can produce. It transforms physics from the study of a single existence into the study of all possible existences, a breathtaking shift in perspective that challenges us to think not just about how our universe works, but why it is the way it is, and what other astonishing realities might be floating in the great beyond. While the theoretical tapestry of invisible fields is rich and compelling, it remains just that, a theory, until we can find tangible, experimental proof. This is where the story moves from the blackboard to the laboratory, as scientists around the world design increasingly ingenious experiments to hunt for the direct signatures of these hidden sculptors. This isn't about inferring their existence from their gravitational effects anymore. This is about trying to catch them in the act, to force them to reveal themselves through their subtle interactions with the world we can see and measure. The quest takes three primary forms: smashing matter together at incredible energies, listening for the faintest whispers from the dark, and performing exquisitely precise measurements of the forces we think we already understand. The mightiest tools in this arsenal are particle colliders, like the renowned Large Hadron Collider. These machines are essentially cosmic microscopes, accelerating particles to near light speed and crashing them together to recreate the unimaginably hot, dense conditions of the very early universe. The goal is to blast a tiny region of spacetime with so much energy that it literally shakes loose something new, a ripple in a field we've never detected, manifesting as a new, transient particle that quickly decays into a shower of familiar ones. The triumphant discovery of the Higgs boson was the ultimate validation of this method, proving that an invisible field could be coaxed into revealing its presence. Now, physicists are using the LHC to hunt for an even more elusive quarry: particles associated with dark matter or with supersymmetry, a theoretical framework that predicts a whole new shadow zoo of particles for everyone we know. Finding any one of them would be a direct detection of a new field and a revolution in our understanding of reality's building blocks. But what if the new fields and their particles don't interact with ordinary matter through anything but gravity? This is the challenge of searching for dark matter. Since it doesn't emit, absorb, or reflect light, we have to get creative. Deep underground, in abandoned mines and tunnels shielded from the constant rain of cosmic rays, physicists have built ultra-sensitive detectors filled with liquid xenon or other noble gases. The idea is to wait in perfect stillness for the extremely rare event where a dark matter particle, drifting through the Earth, might bump into the nucleus of an atom in the detector. That tiny jolt would generate a flash of light or a charge that sensitive instruments could, in theory, pick up. Decades of these experiments have so far come up empty, but the search continues, with next-generation detectors becoming so sensitive that they are beginning to probe the most promising regions of parameter space. The absence of a signal is itself a valuable clue, telling us where the dark matter is not and forcing theorists to refine their models. Another fascinating dark matter candidate points to a different kind of field altogether: the action. This hypothetical particle wasn't invented for dark matter. It was proposed to solve a deep mystery in quantum chromodynamics known as the strong CP problem, which deals with the surprising symmetry in the strong nuclear force. The action is the ripple in a new field that would naturally fix this problem. Fortuitously, these particles would also be produced in copious amounts in the early universe and would have exactly the right properties to be dark matter. Unlike the heavy WIMP, actions would be incredibly light and wave-like. To find them, scientists are building a new class of experiments that are more like giant radio receivers. These detectors use powerful magnets to convert passing actions into microwaves, with the hope of tuning into a specific frequency that would signal their presence. It's a beautiful convergence. A solution to a particle physics puzzle might also be the key to unlocking the mystery of the cosmos's invisible structure. Beyond the hunt for new particles, other experiments test the very fabric of spacetime itself. Precision tests of general relativity are constantly being performed, from lab-based experiments that measure the gravitational attraction between precisely weighed masses to satellite missions that track the orbits of laser-reflecting cubes left on the Moon. Any tiny deviation from Einstein's predictions could be a sign of a new, ultra-weak fifth force or a hint of those extra dimensions proposed by string theory. Meanwhile, the stunning detection of gravitational waves has opened an entirely new window. By carefully studying the signals from colliding black holes and neutron stars, scientists can check if the waves travel at exactly the speed of light and if their shapes match general relativity's predictions perfectly. Any anomaly could point toward a modification of gravity or reveal how gravity behaves in the presence of other hidden fields. Each of these experimental paths, from the colossal energy of colliders to the quiet patience of underground labs and the precise astronomy of gravitational waves, represents a different strategy for confronting the unknown. They are all driven by the same fundamental desire: to move beyond indirect evidence and finally meet the architects of reality face to face. Every null result narrows the possibilities, and every potential signal sends a ripple of excitement through the global scientific community. This painstaking, collaborative effort is how we transform beautiful mathematical ideas into concrete physical truth, inching ever closer to a complete picture of the cosmic masterpiece and the invisible hands that carved it. Now consider the profound and almost unsettling precision of our universe. The strength of gravity, the mass of an electron, the exact energy state of the Higgs field, these aren't just random numbers on a cosmic dial. They are values that appear to be exquisitely, almost miraculously fine-tuned. If any one of them were even slightly different, the consequences would be catastrophic. A slightly stronger gravitational constant, and stars would burn through their fuel in a cosmic blink, leaving no time for planets to form or life to evolve. A slightly weaker nuclear force, and the protons in the early universe would never have fused together, meaning no elements heavier than hydrogen, no chemistry, and no us. This incredible balance is what leads us to the Anthropic Principle, a concept that bridges the gap between physics and philosophy, asking not just how our universe works, but why it is the way it is in the first place. At its heart, the Anthropic Principle is a simple statement of observation. The fundamental constants and laws of our universe must be compatible with the existence of observers, because here we are, observing it. We could not possibly find ourselves in a universe incapable of producing conscious life. This isn't an explanation in itself, but rather a filter through which we must view any theory about the cosmos's origin. It forces us to recognize that our universe is not a random sample. It is a very special one, selected by the fact that it allows for its own contemplation. The invisible fields we've been exploring, the Higgs, the inflaton, the fields behind dark energy, are the master tuners of this cosmic instrument. Their specific values are the settings that determined whether the symphony of the universe would be a rich, complex composition or just a single, silent note. Imagine the Higgs field for a moment as a cosmic dial governing mass. In our universe, it's set to a very specific value that allows for atoms, molecules, and ultimately, galaxies and brains. But what if that dial were turned just a fraction higher? Particles would become so heavy and sluggish that they would instantly collapse into black holes, creating a universe of nothing but gravitational singularities. Turn the dial the other way, making the Higgs value weaker, and particles would have no mass at all, zipping around at the speed of light in a chaotic, structureless fog. The inflaton field, which drove the rapid expansion of the early universe, had to possess an incredibly specific potential energy to stretch space just enough to smooth it out without tearing every quantum fluctuation apart beyond repair. The field responsible for dark energy presents the most dramatic fine-tuning problem of all. Its energy density is absurdly small compared to theoretical predictions, yet if it were even marginally larger, the accelerated expansion would have ripped apart any incipient galaxies before they could ever form. This incredible fine-tuning presents a major puzzle. is it merely a spectacularly unlikely accident, a 1 in a trillion cosmic lottery ticket that we happen to win? This is where the Anthropic Principle moves from a simple observation to a controversial interpretive framework. One compelling resolution comes from the multiverse hypothesis. If our universe is just one bubble in a vast, perhaps infinite, multiverse, then each bubble universe could have randomly different values for its fundamental constants and field strengths. In an infinite landscape of possibilities, the vast, overwhelming majority of these universes would be stillborn or barren, lifeless voids where the fields never align to create stability. But by sheer probability, a tiny fraction of universes would, by pure chance, have the perfect combination of field values to allow for stars, planets, and life. We, of course, can only exist in one of those rare, habitable bubbles. In this view, the fields are not fine-tuned by any design. We are simply the inevitable inhabitants of a rare oasis that meets the strict requirements for our existence. The alternative to this cosmic lottery is the possibility of a deeper, yet to be discovered law of physics that naturally determines the values of these fields. Perhaps the 20 or so free parameters in the standard model are not free at all, but are the inevitable outcome of a more fundamental, unified theory, a theory of everything that would show why the constants must have the values they do. This would be the most satisfying solution for many physicists, as it would replace the appearance of miraculous fine-tuning with a deterministic, elegant equation. The Anthropic Principle challenges us to find this deeper law, or to accept a much wider and stranger reality than we ever imagined. It suggests that the invisible sculptors of spacetime are not arbitrary artists, but are either constrained by a meta-law we have yet to grasp, or are part of a cosmic evolutionary process where countless universes are born, most dying instantly, and only a select few, like ours, possessing the right recipe to look back and wonder at their own improbable existence. While the quest to understand the invisible architects of reality is driven by a fundamental desire to comprehend our universe, this profound knowledge rarely remains confined to the realm of pure theory for long. History shows us that every deep leap in our understanding of nature's hidden forces has eventually unleashed a wave of technological transformation that reshapes human civilization. The discovery and mastery of electromagnetism didn't just answer questions about light and magnetism. It gave us the electric grid, global communication, and the digital revolution. In the same way, unraveling the mysteries of quantum fields, space-time curvature, and vacuum energy could open doors to technologies that feel like they belong in the realms of science fiction, poised to become the science fact of tomorrow. Consider the furious activity of the quantum vacuum, that seething sea of virtual particles popping in and out of existence. Right now, this energy is locked away, its potential untapped. But what if we could find a way to interact with it, to somehow extract even a minuscule amount of this ubiquitous zero-point energy? The concept of harvesting energy from the vacuum fluctuations of space itself is one of the most speculative yet tantalizing prospects. While the engineering challenges are monumental and it may forever remain beyond our grasp, the mere possibility drives research into novel materials and extreme physical regimes. The pursuit forces us to push the boundaries of nanotechnology and superconductors, leading to accidental discoveries and incremental advancements in energy storage and efficiency that benefit society long before the ultimate goal is ever reached. A much more immediate technological revolution is already brewing in the realm of quantum field manipulation, quantum computing. Unlike classical computers that use bits as simple zeros or ones, quantum computers use qubits. A qubit can be in a state of superposition, representing both 0 and 1 simultaneously, and multiple qubits can become entangled, their states inextricably linked. This isn't just a faster computer, it's a different kind of computer altogether, one that operates on the principles of quantum field theory. By precisely controlling the quantum states of these qubits, essentially orchestrating the behavior of their underlying fields, we could solve problems that are completely intractable today. This could mean designing entirely new materials molecule by molecule, discovering life-saving drugs by simulating their interactions with incredible accuracy, or breaking the encryption that currently secures the internet, necessitating an entire new paradigm of quantum cryptography. The quantum computer is a direct application of our hard-won knowledge of the quantum world, a machine that doesn't just calculate but harnesses the bizarre laws that govern reality at its smallest scales. The implications extend beyond our planet, reaching for the stars. Our current methods of propulsion are painfully slow for interstellar travel. A journey to the nearest star would take tens of thousands of years with conventional technology. But if we truly understand how mass and energy warp spacetime, could we invent a way to manipulate that geometry for travel? This is the dream behind theoretical concepts like the Alcubierre warp drive. The idea is not to propel a ship through space faster than light, but to instead contract spacetime in front of the vessel and expand it behind, effectively creating a wave that the ship rides within. The space itself would move, bypassing the universal speed limit. This would require the generation and control of astronomical amounts of energy, possibly of a kind we don't yet understand, like negative energy density. While this remains a highly speculative idea on the drawing board of physicists, it exemplifies how a deep understanding of gravity's workings can inspire audacious thinking. The research into such concepts alone pushes forward our knowledge of general relativity, materials science, and energy systems. Even without Star Trek-style warp drives, the study of these invisible fields is a powerful engine for innovation here and now. The desperate need to detect the incredibly faint signals of gravitational waves drove the creation of LIGO, an instrument of almost impossible sensitivity. The technologies developed for stabilizing its lasers, isolating its mirrors from vibrations, and processing the enormous amounts of data have found applications in everything from precision manufacturing to medical imaging. The hunt for dark matter particles has driven the development of ever more sensitive detectors and novel materials that could lead to new types of sensors for security or geology. The mathematical tools developed to describe higher dimensions in string theory have found unexpected uses in fields like economics and data analysis, helping to visualize complex problems. The pursuit of fundamental knowledge, even in its most abstract form, consistently acts as a catalyst, forcing us to invent better tools, better materials, and better ways of thinking that inevitably ripple out to benefit the entire world. This relentless drive to understand the cosmos doesn't just tell us about the universe out there, it provides the keys to building a better future right here. This journey through the invisible forces shaping our universe inevitably leads us to a profound and deeply personal question, one that has echoed through the ages from ancient philosophers to modern physicists gazing at their equations. What is reality, truly? We navigate our daily lives with a confident sense of the world around us, solid ground beneath our feet, the dependable warmth of the sun, the vastness of the night sky. It all feels so tangible, so real, yet our exploration reveals that this tangible reality, the world of our senses, might be just the surface layer, the visible tip of a much deeper and more mysterious iceberg. The discovery that everything from the mass of an atom to the fate of a galaxy is governed by invisible, pervasive fields challenges the very foundations of what we consider to be real. Are these fields themselves the ultimate reality, or are they simply incredibly useful mathematical tools, a language we've invented to describe patterns we observe? This isn't just a semantic debate, it strikes at the heart of what it means to know something. Philosophers of science have long grappled with this distinction. On one hand, you have the realist perspective, which argues that these quantum fields are as real as the chair you're sitting on, even if we can't see or touch them directly. Their reality is confirmed by the undeniable, predictable effects they produce. We don't need to see the wind to believe in it, we see the trees bending. In the same way, we see particles gaining mass from the Higgs field and light bending from the curvature of spacetime. The fields are the causal agents behind the phenomena. The opposing view, instrumentalism, suggests that fields are not necessarily real entities, but are incredibly powerful models, human inventions that allow us to predict outcomes with stunning accuracy. In this view, asking if the electromagnetic field is real is like asking if the number 5 is real. It's a concept that helps us organize and manipulate the world, but it may not be a thing in and of itself. This debate forces us to confront what we mean by existence. Does something only exist if it can be directly measured, or does its power to shape the measurable world grant it a form of reality? This conversation bridges the cold, hard data of science with the timeless questions of metaphysics, pushing us to consider whether the reality we experience is fundamental or emergent. Is the solidity of a table a primary, inherent quality, or does it emerge from the frantic interactions of quantum fields and forces that are mostly empty space? The table feels solid because the electromagnetic fields of the atoms in your hand are repelling the electromagnetic fields of the atoms in the table, a reality built entirely from invisible interactions. This suggests that our everyday experience is a kind of useful illusion, a dashboard of simplified readings that our brain presents to us so we can navigate the world, while beneath the surface, a far more complex and alien machinery is at work. The universe might be less like a giant physical clockwork and more like a vast interconnected computation or a network of information, with space-time and matter being the projected output. Engaging with these questions doesn't provide easy answers, but it cultivates two essential qualities, humility and wonder. Humility, because it reveals the limits of our perception and our current understanding. We are like deep-sea creatures trying to comprehend the concept of water. We are so immersed in this reality that it's difficult to perceive its true nature. And wonder, because the sheer elegance and complexity of this hidden architecture is breathtaking. The fact that we can use mathematics, a product of the human mind, to uncover these deep secrets of the cosmos is a miracle in itself. It suggests a mysterious harmony between our minds and the universe, a connection that is as profound as it is unexplained. Recognizing that the true architects of reality may forever elude our full comprehension is not a surrender. It is an invitation to a never-ending journey of discovery, a constant reminder that the universe is far stranger, more beautiful, and more mysterious than we could ever have imagined. Long before we had equations for quantum fields or detectors for gravitational waves, humanity looked up at the star-filled sky and sensed that there were hidden hands at work. We have always lived in a world shaped by forces we could not see, and our ancestors crafted stories to explain them. They saw gods in the sun and moon, felt spirits in the wind and sea, and imagined a celestial realm where powerful beings orchestrated the seasons and the motions of the planets. This innate desire to personify the invisible is a fundamental part of our history, a primal response to a cosmos that felt both ordered and mysterious. The ancient Greek concept of the ether, a fifth element that permeated the heavens and carried the planets in their perfect circles, was an early scientific attempt to give a name to the medium through which these unseen forces acted. It was a placeholder, a best guess based on the philosophy and observation of the time, but it sprang from the same deep well of curiosity that drives our physics today. What's truly remarkable is how these ancient intuitions sometimes echo the shape of our modern theories, even if their substance was entirely different. Many cultures envision the universe as a living, breathing entity or a great woven tapestry, a single, interconnected whole. This isn't so far from our current understanding of space-time as a dynamic, flexible fabric. The concept of a universal medium, a plenum that fills the void, is a direct ancestor to our quantum field theory. The major shift hasn't been in the core impulse to find these architects, but in our methods. We've traded myth and pure philosophy for the rigorous language of mathematics and the unwavering standard of empirical evidence. The ether was a philosophical concept. The Higgs field is a mathematical entity whose existence was confirmed by a massive international experiment. We've moved from attributing the motion of a planet to the whims of a god to calculating its exact path using the geometry of curved space-time. The quest is the same, but our tools have become infinitely more powerful and precise. This historical continuity adds a rich layer of meaning to our scientific pursuit. It frames our search for dark matter and dark energy not as a cold, detached calculation, but as the latest chapter in an epic, timeless human story. We are still telling stories about the universe, but now our narratives are written in the language of tensor calculus and backed by data from telescopes that peer back to the dawn of time. Recognizing this link fosters a profound sense of connection to the thinkers and dreamers who came before us. The philosopher contemplating the ether and the physicist running simulations of the inflattened field are engaged in the same essential endeavor, a deep and abiding need to map the unknown, to find our coordinates in the cosmos, and to understand the nature of the stage upon which our existence plays out. This perspective transforms the history of science from a simple chronology of discoveries into a deeply human drama. It allows us to appreciate the journey itself, the wrong turns, the brilliant leaps of intuition, the gradual refinement of ideas as a fundamental part of the discovery. The outdated concept of the ether wasn't a failure. It was a necessary stepping stone, a way of thinking that had to be proposed, explored, and ultimately disproven to clear the path for the theory of relativity. Every myth and every discarded theory was a response to the available evidence and a reflection of the human imagination reaching as far as it could. This long arc of inquiry reminds us that our current models, for all their predictive power, are also provisional. They are the best stories we have for now, built to fit the evidence we can gather, and they will likely be refined or even revolutionized by future generations who will see further than we can. Ultimately, this cultural and historical context does more than just teach us about the past. It enriches our present exploration. It adds a dimension of humility and wonder to the hard science. It reminds us that behind every equation is a very human desire for meaning and connection. As we use particle colliders to probe the Higgs field and satellites to map the cosmic microwave background, we are participating in a tradition that stretches back to the first stargazers. We are continuing the conversation they started, using new vocabulary but asking the same essential questions. This connection to our shared history makes the scientific endeavor feel less like a solitary, technical exercise and more like a collective, ongoing pilgrimage, a continuous, collaborative effort to read the cosmic blueprint and finally meet the invisible architects we have always known must be there. Bringing these mind-bending concepts down to earth is one of the most vital and creative challenges in modern science. How do you explain something as abstract as a quantum field or the curvature of spacetime to someone without a PhD in theoretical physics? The answer lies not in simplifying the ideas, but in making them relatable, transforming complex mathematics into compelling stories and vivid mental images that anyone can grasp. This is the art and science of science communication, and it's absolutely essential for turning public curiosity into genuine understanding. Think of it like trying to describe the color red to someone who has been blind since birth. You can't just show them a wavelength on a chart. You have to talk about the warmth of the sun on their skin, the feeling of excitement, the taste of a ripe strawberry. You build a bridge from their existing experience to the new concept. Explaining the Higgs field works the same way. You start not with equations, but with a metaphor that clicks, a crowded party room where an important person moves slowly, surrounded by admirers, while a nobody can zip through the crowd unnoticed. That resistance, that social friction, is a powerful analog for how particles gain mass by interacting with the Higgs field. It's not a perfect one-to-one comparison, but it builds an intuitive scaffold for the real physics to later attach itself to. This is where the power of analogy truly shines. The universe is full of patterns that repeat at different scales, and a good analogy leverages that. To explain how gravitational waves stretch and compress space-time, you can use the classic image of a mesh net. Place a heavy bowling ball in the center, and it creates a dip. Now jiggle that bowling ball rapidly. The ripples that travel outward through the net, temporarily distorting the grid as they pass, are a direct and intuitive representation of how a merging black hole sends ripples through the cosmic fabric, momentarily squeezing and stretching the distances between stars. Visualizations take this a step further, transforming data into experience. The first image of a black hole's shadow wasn't just a pretty picture, it was a story. The dark circle surrounded by a fiery, lopsided ring instantly communicated the intense gravity warping light itself, a concept that could take pages of text to describe. Interactive planetarium shows and museum exhibits allow people to literally play with these ideas, using touchscreens to warp a virtual space-time sheet or adjust the strength of a simulated dark energy field to see its effect on a virtual universe. These tools don't dumb down the science, they translate it into a sensory language that bypasses the barrier of complex math and allows for a direct, visceral comprehension. At its heart, this entire endeavor is about storytelling. The history of science is an epic narrative filled with mystery, rivalry, brilliant insights, and stunning revelations. Framing the discovery of the Higgs boson as a decades-long hunt for a ghostly particle, involving the construction of the world's largest machine in an underground ring, is far more captivating than just stating its properties. Talking about Vera Rubin's struggle to be heard as she pieced together the evidence for dark matter, personalizes the science and highlights the human drama behind the data. These stories provide context and emotional hooks, making the information memorable. They show that science isn't a static set of facts in a textbook, but a dynamic, ongoing detective story, and everyone is invited to try to solve the mystery. This approach fosters a sense of wonder and connection, the same feeling of awe that comes from gazing up at a starry night sky, but now augmented with a deeper understanding of the incredible forces at work behind the scenes. The ultimate goal of all this effort is to build a foundation of scientific literacy that empowers people to navigate the modern world. The technologies that shape our daily lives, from the GPS in our phones that must account for Einstein's time dilation to the medical MRI machines that rely on quantum spin, are all direct applications of these fundamental fields. Understanding where these technologies come from is more than just trivia. It helps us make informed decisions about the future, from climate science to genetic engineering. More importantly, it cultivates a rational, evidence-based way of thinking that is crucial for a healthy society. By making the invisible sculptors of reality accessible, we do more than just teach physics. We inspire a new generation of diverse thinkers, artists, engineers, and yes, scientists, to look at the universe with fresh eyes and ask the next great questions. Their unique perspectives, born from this foundational wonder, will be the key to unlocking the mysteries we can't even yet imagine. Yet this grand quest to map the invisible is not confined to the realm of physics alone. It is a profoundly collaborative endeavor, a symphony of different disciplines, each playing a crucial part in deciphering the cosmic score. The language of these hidden fields is written in mathematics, a dialect of such abstraction and beauty that it often predicts reality long before we can observe it. The equations of quantum field theory and general relativity are expressed in the intricate grammar of differential geometry and topology, where the curvature of spacetime is not just a metaphor but a precise, calculable property. Concepts like Calabi-Yau manifolds from pure mathematics provide the possible shapes for string theory's hidden dimensions, demonstrating that the tools for understanding the universe's deepest architecture are often forged in the abstract fires of numerical reasoning, waiting for their moment of application. This is not a one-way street. The bizarre physical realities uncovered by cosmology constantly present new and fascinating challenges for mathematicians, pushing the creation of entirely new forms of calculation and visualization to keep pace with the strange truths of the cosmos. This mathematical foundation is brought to life through the raw power of modern computing, simulating the evolution of the universe from the quantum fluctuations imprinted by inflation to the formation of the vast cosmic web of galaxies, is a task of such monumental complexity that it demands the world's most powerful supercomputers. Researchers create virtual universes in silicon, running countless simulations with slightly different parameters for dark matter and dark energy. They watch as their digital Big Bangs unfold, comparing the resulting galactic structures to the maps we've painstakingly observed through telescopes. This process of cosmic cartography is a dialogue between the theoretical and the observational, with algorithms acting as the crucial interpreter. Without these advanced computational techniques, our ideas about how dark matter scaffolds the universe would remain untested hypotheses. The field of data science itself is being revolutionized by this work, as physicists develop novel machine learning algorithms to sift through the unimaginably large datasets produced by instruments like the James Webb Space Telescope, training artificial intelligences to recognize the subtle gravitational lensing effects of invisible matter, or to classify the types of galaxies that emerge. Different physical laws, perhaps most surprisingly, the influence of these invisible fields extends its reach into the very science of life itself. Biology is no longer just the study of tangible molecules and cellular structures. It is increasingly recognized as a science of forces and fields. Within every one of our cells, intricate electromagnetic fields guide processes like cell division and migration. The very way our neurons fire and communicate is a bioelectrical phenomenon, a symphony of ion exchanges creating localized fields that form the physical basis of our thoughts and consciousness. Some researchers even explore the controversial idea that quantum phenomena, like coherence and entanglement, might play a role in biological processes such as photosynthesis or avian navigation, suggesting that the same fundamental fields that govern the cosmos might also be subtly at work within living organisms. This doesn't diminish the wonder of biology, it elevates it, framing life not as a separate phenomenon from the physical universe, but as an incredibly complex and beautiful expression of its most fundamental laws, a local concentration of information and energy dancing to the tune of universal fields. This cross-pollination of ideas is the engine of modern discovery. A physicist's insight into symmetry breaking can provide a biologist with a new model for understanding the sudden differentiation of stem cells. A computer scientist's algorithm for detecting faint patterns in noise can be adapted by a cosmologist to find the signature of primordial gravitational waves in the cosmic microwave background. These interdisciplinary connections reveal a powerful and unifying truth. The sculptors of spacetime are not isolated actors. They are part of a broader tapestry of natural law, a set of universal principles that express themselves in different ways at different scales, from the frantic dance of quantum particles to the stately whirl of galaxies, and even within the intricate processes of a living cell. By tearing down the artificial walls between subjects, we don't just accelerate progress, we gain a more holistic, profound, and ultimately more beautiful picture of a reality that is deeply, fundamentally, and wonderfully interconnected. And just as we begin to map the contours of these invisible forces, our tools for cosmic cartography are undergoing a revolution of their own, poised to peer deeper into the shadows than ever before. The next decade promises to be a golden age of discovery, driven by a new generation of observatories and experiments designed to interrogate the universe's hidden architects with breathtaking precision. Imagine the James Webb Space Telescope not just as a successor to Hubble, but as a cosmic time machine, its infrared gaze piercing through clouds of dust to witness the very first galaxies being born. By studying this primordial era, we can trace the gravitational influence of dark matter at its most potent, watching how it pulled those early collections of stars and gas into their distinct shapes. Webb's detailed spectroscopy will also analyze the light from the most distant supernova, offering an independent and exquisitely precise measure of how dark energy has behaved over the vast expanse of cosmic history, potentially revealing if its strength has changed over billions of years. But our vision is not limited to light. The success of LIGO and Virgo in detecting gravitational waves has opened an entirely new sense, and the next phase of this exploration is already underway. The Laser Interferometer Space Antenna, or LISA, is a planned constellation of 3 spacecraft that will fly in a vast triangular formation, millions of kilometers apart. By precisely monitoring the distance between them with laser beams, LISA will form a gravitational wave observatory of staggering scale, sensitive to frequencies far lower than any ground-based detector can achieve. This will allow it to hear the low rumble of entirely new classes of events, like the slow, in-spiral dance of supermassive black holes at the hearts of merging galaxies, events that can shake the fabric of space-time for millions of years. By studying these waves, we could detect subtle distortions that reveal the properties of the space-time they traveled through, potentially sensing the presence of extra dimensions or other exotic fields that alter gravity's pure tone. On the theoretical front, the quest for a unified theory of quantum gravity continues to accelerate, guided by profound ideas that are slowly moving from pure mathematics toward testable predictions. Supersymmetry, a concept that posits every known particle has a heavier superpartner, remains a compelling, though as yet unproven, framework. If validated by a future collider, it would not only solve several nagging problems in the standard model, but could also provide a perfect candidate for dark matter in the form of the lightest supersymmetric particle. Similarly, the holographic principle and the lessons from the AD/S/CFT correspondence are providing physicists with a powerful new dictionary for translating problems of gravity into problems of quantum physics, offering fresh avenues to tackle puzzles like the black hole information paradox. These are no longer just abstract speculations. They are concrete guides shaping the design of new experiments and the questions we ask of the cosmos. The true excitement, however, lies in the potential for a complete surprise, a discovery that forces us to rewrite the textbooks entirely. Our current model, for all its success, is built upon two mysterious pillars: dark matter and dark energy. It is entirely possible that the next great leap will not be the detection of a specific dark matter particle, but a paradigm-shifting observation that shows our understanding of gravity itself is flawed on cosmic scales. A single anomalous observation from a telescope like the Vera Rubin Observatory, which will conduct an unprecedented survey of the entire southern sky, could be the thread that unravels the whole tapestry. Or perhaps a tabletop experiment probing the quantum nature of gravity will reveal a discrepancy so fundamental that it points toward a reality where space and time are not continuous but are composed of discrete, indivisible units. This relentless, multi-pronged pursuit, combining immense telescopes, sensitive underground labs, powerful colliders, and brilliant theoretical insight, guarantees that our story of the cosmos is nowhere near its final chapter. We are on the cusp of revelations that will not just add new details to our map, but will undoubtedly force us to redraw the map itself, revealing a universe far stranger and more wonderful than we currently have the capacity to imagine. Yet as we reach for these cosmic truths, we must also pause to consider the immense responsibility that comes with such profound knowledge. The power to understand and potentially manipulate the fundamental fields of the universe is not a neutral force. It carries with it deep ethical questions that we are only beginning to confront. Imagine a future where the principles behind warping space-time are not just theoretical concepts but applied technologies. The same physics that describes how mass curves the cosmic sheet could one day inform the development of advanced propulsion systems. Perhaps even theoretical warp drives that contract space ahead of a spacecraft and expand it behind. While this remains firmly in the realm of speculation, the mere possibility forces us to ask who would control such technology and for what purpose. The societal impacts would be staggering, potentially redefining global economics, access to space, and even the balance of geopolitical power. The knowledge itself could become a dividing line, creating a new class of haves and have-nots separated not by wealth alone, but by their access to understanding and leveraging the very fabric of reality. This demands a framework of careful oversight and international dialogue long before such capabilities are even remotely feasible, ensuring that these discoveries serve to unite and elevate humanity rather than create new forms of inequality or conflict. This leads to a broader consideration of how the pursuit of this knowledge is structured and who gets to participate. Fundamental physics has historically been an endeavor dominated by a handful of wealthy nations that can afford the immense costs of particle colliders and space telescopes. While international collaborations like the Large Hadron Collider are a step in the right direction, true inclusivity requires actively dismantling barriers to entry for researchers from developing nations and ensuring that the data and insights gleaned from these monumental projects are global public goods, not walled off by proprietary interests or national security concerns. The questions we are asking about the universe belong to all of humanity, and the answers should benefit everyone equally. This means proactively building partnerships, sharing resources, and fostering a new generation of scientists from diverse backgrounds and cultures. Their unique perspectives are not just a matter of equity, they are a critical component of scientific progress. The next revolutionary insight into dark energy or quantum gravity might come from a mind that would otherwise never have the opportunity to engage with the problem, and we simply cannot afford to lose those voices. Furthermore, we must remain vigilant against the potential for harmful applications, even in seemingly abstract research. History is littered with examples of pure scientific discoveries being co-opted for destructive purposes. The equations that describe the stability of stars also unlock the terrible power of thermonuclear weapons. As we delve deeper into the energy of the quantum vacuum or the nature of high-energy field interactions, we must establish clear ethical guidelines and norms within the scientific community. This involves a continuous process of reflection, asking not only can we, but also should we at every step of the way. It requires robust engagement with the public, demystifying the science and making the potential risks and benefits transparent so that societal values can help guide the direction of research. The goal is to foster a culture of scientific stewardship where the awe-inspiring privilege of uncovering the universe's deepest secrets is matched by a profound commitment to using that knowledge wisely, ensuring that our journey to understand the invisible sculptors of reality ultimately serves to create a more just, peaceful, and enlightened world for all. Our journey through the invisible field sculpting space-time reveals a universe far more intricate and mysterious than it appears. We began by thinking of reality as a stage where events simply play out, but now we see the stage itself is alive, dynamic, and constantly being shaped by forces we are only beginning to comprehend. Gravity, that most familiar of sculptors, bends the paths of planets and light, yet it cannot work alone. It requires silent partners, dark matter to provide the hidden scaffolding for galaxies, and dark energy, that enigmatic force stretching the very cosmos apart at an ever-increasing pace. But the story goes even deeper, into the quantum realm where particles are mere ripples in eternal, everywhere present fields. The Higgs field gives substance to matter. The inflattened field may have forged the universe in a fiery burst of expansion, and the ceaseless churn of quantum fluctuations might even hold the key to the vacuum energy fueling our universe's fate. This isn't just a collection of isolated ideas, it's a symphony of interaction. The same quantum whispers that governed the birth of particles were stretched to cosmic proportions, becoming the seeds for galaxies, stars, and eventually us. The discovery of gravitational waves lets us feel the tremors from colossal collisions, a direct sensation of spacetime itself ringing like a bell. And theories like the Holographic Principle suggest that this entire four-dimensional universe we experience might be a projection from a deeper, two-dimensional reality encoded with information. Each of these concepts challenges our perception, pushing us to accept that the true foundations of reality are not solid things, but relationships, energies, and information. We are learning that to understand the cosmos, we must look beyond what is visible and engage with the invisible architects that dictate the laws of existence itself. As we continue to probe these mysteries with ever more sensitive telescopes, colliders, and detectors, we are not merely satisfying a passive curiosity. We are actively participating in one of the greatest stories ever told, the unraveling of our own origins and our place in the cosmos. Every new observation, every theoretical breakthrough adds another brushstroke to this magnificent, evolving masterpiece. We are both the audience and the artists, observers and participants in a reality that is forever being sculpted. This quest binds us to every human who has ever looked up at the night sky in wonder, and it connects us to the future generations who will build upon the knowledge we uncover today. The greatest takeaway is that the universe is not a static, completed work. It is a dynamic, ongoing creation, and our urge to understand it is an essential part of its beautiful, unfolding narrative. If this exploration of space-time sculptors captivated you, please consider giving this video a like and sharing it with someone else who marvels at the universe's grand mysteries. Your share is what helps this channel grow and spread the wonder of discovery. To join us on our next journey into the cosmos, be sure to subscribe to the channel and tap that bell icon so you never miss a new release. We are constantly working to bring you more deep dives into the fundamental forces and hidden phenomena that shape our reality. I would also absolutely love to hear what you thought about these ideas. Did a particular concept blow your mind? Do you have a burning question about dark energy or a different take on quantum fields? Please take a second and drop your thoughts and questions in the comments section below. This is a conversation, and your insights make it richer for everyone. Together, let's keep pulling on the threads of the cosmos, unraveling the universe's greatest secrets one field at a time. Thank you so much for watching and for your curiosity. Until our next adventure, keep looking up and